very good morning. Welcome dear student friends, and today we are going to focus on Smart Grid Basic to Advanced Technology Module 9 Lecture 1. And the main agenda today is to focus on demonstration of solar power generation. I request all of you to concentrate and let us not be in hurry and make sure that you complete the full module in one go for better understanding. The test bed which we are going to use for the demonstration of solar generation, I wish to highlight here the DC power from the PV panel is converted to AC power through the polytronic interface, which is basically called as inverter. The solar inverter can operate either in grid connected mode, also called utility mode, or islanded mode, can also be popularly known as stand-alone mode operation. And in this course, only the hardware demonstration of grid connected mode of solar inverter is considered. As per the grid codes, the inverter operating in grid connected mode is expected to inject high quality currents, followed by providing grid support standards. Now, when you look into the hardware setup of a single stage inverter and its control system, resembles the one in this schematic slide. The single stage solar inverter is represented here along with its control system. It has all the control loops such as the MPPT loop, inner current loops, and grid synchronization loop, which is essential to solar inverter operation. Let us see more details on the inverter connections and its control in the coming slides. Let us focus on the test bed description. The test bed which we are going to use for the demonstration of solar generation, the components of the test bed are programmable DC source, which can emulate the characteristic of PV panel, and the next one is the grid emulator, which acts as an interface to connect the inverter to the grid. The grid emulator takes the power from the inverter and feed it to the distribution system. Now, the next component is semicron IGBT stack, which acts as inverter and performs the single stage power conversion from the PV emulator to the grid. Now, we have the voltage and current sensor circuit boards along with signal conditioning circuits, and for the test bed, the control system is implemented in the Opal RT platform. An inverter which is controlled by using Texas DSP will also be demonstrated in the upcoming lectures. We have an MCB which forms the PCC to connect and disconnect the inverter from the grid. Now, let us see the details of these test bed components. To start with, let us focus on programmable DC source. The rating of the model that we are using for our demonstration has a power rating of 5 kilowatt and a voltage rating of 600 volts. It is basically a single channel one. It is directly connected to the DC bus of the 3-phase inverter in our test bed. Now, when you focus on the characteristic of a solar cell, we have used an emulator which allows us to set the maximum power point voltage, maximum power point current, open circuit voltage, PV power, and so and so, thereby emulating the PV and IV characteristic of a solar cell or array as shown in the slide. It is the duty of the inverter to track the maximum power point by delivering power to the grid. Semicron IGBT stack, we can see here in the video, we have shown a single IGBT stack which has semicron switches and diodes. Before talking about the rating of the IGBT stack, let us look into the circuit diagram of the stack. It mainly consists of two sections. One is the 3-phase diode bridge rectifier towards the left, and in the right it is the 3-phase 4-wire inverter bridge circuit. The 3-phase diode bridge rectifier has the input AC voltage rating of 415 volt and DC output voltage of the rating 560 volts. The inverter bridge has DC input voltage rating of 700 volt and AC output voltage rating of 415 volt RMS along with 30 ampere output current. One important thing to be noticed here is that the DC input capacitor or the DC bus should be rated to more than peak of the grid voltage such that the power can be transferred from the DC side to the AC side. The basic understanding here that until unless you create a voltage difference, it is not possible to transfer reasonable amount of power from one point to the other. For 415 volt RMS AC grid, peak voltage is around 586 volt and the rating of the DC bus is 700 volt. This ensures that there is a sufficient margin for the inverter operation, and in our demonstration we kept higher operating margin by considering the maximum DC bus voltage of 400 volt DC and 110 volt RMS AC grid. The IGBT module used here is SKM75GB12T4. You can see here we have an IGBT module shown in the video, where in terms of the rating it is not same as the one used in the IGBT stack, but physically it look quite similar. Here one module can form an inverter leg, as each module consists of 2 IGBTs along with the corresponding body diodes. Hence, 4 such modules are used to form a 4-leg inverter. The rating of the IGBT module used in the stack can block voltage up to 1200 volts and also can carry a nominal load current of 75 amperes. It supports switching frequency up to 20 kilohertz. These modules are attached to the aluminum heat sink, which can be seen here to dissipate the heat. These IGBT modules are popularly used in solar inverters, motor drives as well as UPS applications. Within the stack, forced air cooling through fan is also provided for carrying out fast cooling. Also, in the inverter section, one can notice that each IGBT module is provided with the snubber capacitors, those are connected in parallel to provide protection against the high dB upon dt. The trigger that IGBT switches gate drivers are required to convey the pulses received from controller to the gate terminal of the IGBT. Each driver can trigger one module. Hence, 4 numbers of Skyper 32R gate drivers are provided. and these drivers also require isolated DC input of plus or minus 15 volt to operate. Moreover, these drivers have inbuilt dead band protection as well. At the DC link input of the inverter bridge, we have earlier seen two semicron make electrolytic capacitors are connected in series whose ratings are 4700 microfarad, 700 volt each. Across each capacitor, bladder resistors are connected to discharge the stored energy in the capacitors when the inverter is not in operation. Apart from this, the IGBT module also has an inbuilt thermal trip protection feature in case if device exceed the threshold temperature. There are 4 legs in the inverter. For our application, we are using only 3 legs because we are demonstrating solar generation for balanced 3-phase 3-wire system. Moreover, we are talking about only the single stage conversion. It is also possible to use the same setup for 2-stage conversion as well. The leftover 4th leg can be used to build the DC-DC boost stage. And how can we do that? Let us understand in detail. Let us say we have 4-leg inverter, so that the legs consisting of R, Y and B phases are utilized to rig up 3-phase 3-wire inverter, and this will be the DC AC stage. Now, to build DC DC stage, we can use the unused 4th leg as mentioned earlier in my previous description. And currently we can see the actual DC DC boost converter circuit which has been shown here, and how to build using this IGBT stack along with the DC DC inverter. We can connect positive terminal of PV input to an external high frequency inductor whose other end is connected to the point N. The lower side IGBT T2 can be used as switch which is connected between point N and DC bus negative. The body diode of IGBT T1 can be used as diode for the freewheeling action when T2 turns off. Then the cathode of this diode is connected to the DC bus capacitors. This is how we can build DC DC stage as well as DC AC stage using a single IGBT stack. Now, let us move to the test bed understanding. Next component of our test bed is the voltage and current sensor circuit. We use Hall effect based sensors for both voltage and current sensing. LEM make voltage transducer. LV25P is used for voltage sensing, while the current transducer LA55P is used for current measurement. Also, the circuit board has plus or minus 12 volt DC power supply circuit to power up the ICs present in the sensor board. Apart from these LEM sensors, the sensor circuit for voltage and current measurement also consists of signal, conditioning circuit and level shifting circuits. Now, moving to the component of the test bed which is quite important, so called Opel RT. The control system of the inverter is implemented in Opel RT, which runs on RTLab software by calling the MATLAB Simulink files. Opal RT is basically a real time simulator which can be used to perform real time simulation using MATLAB / Simulink as well as performing rapid control prototyping by implementing the power electronic converter control. First, we can simulate the system in MATLAB Simulink. Later, remove the plant from the simulation file retaining the control system, then implement the plant using real hardware and finally call the simulation file with the inverter control from RTLab. To perform rapid control prototyping, we need to access the analog input output pins, which we generally call them as analog input outputs. The model of Opal RT that we are using is OP5700. In the video, we can see 16 analog inputs, 16 analog outputs, 32 digital inputs and 32 digital outputs. The output and input voltage range of analog pins is plus or minus 16 volts. Accordingly, the voltage and current sensor circuits are designed such that their output voltage range is not exceeding the voltage range of analog input pins of the Opal RT under any circumstances. The PWM pulses generated from the control system can be taken out of the digital output pins with magnitude of either plus 5 volt or plus 12 volt by connecting an external DC source to the specific pins of the digital out. Now, the next attempt is to sense and PWM outputs. Using these analog input pins, we can send the 3-phase voltage and current signals sensed using sensor circuit to the control system. So, we need at least 3 input pin for AC voltage and 1 for the DC voltage, 3 pins of AC current and 1 pin for the DC current sensing. In total, we will be using 8 analog input pins. Similarly, the PWM pulses generated by the control system need to be taken out of the digital output pins of the Opal RT. Now, these level shifted PWM pulses which are generated in the order, the digital output pins 1 to 6 gives PWM pulses. Digital output pins 1 and 2 generate complementary pulses for the IGBT module of the R phase. So, these output pins 1 and 2 are connected to the input pins of the Skyper 32R gate driver, which is dedicated to the R phase of the IGBT module. Similarly, the digital output pins 3, 4 and 5, 6 are connected to the respective gate driver of that phase. These gate pulses are of 0 to 12 volt magnitude with respect to a common potential external DC source negative in our case. However, the gate terminal of IGBT requires positive and negative voltage to turn on and turn off the device. For this, we can utilize the plus minus 15 volt DC power supply board present in the voltage and current sensor board. Therefore, each Skyper 32R driver has 5 inputs. 2 inputs are dedicated for PWM pulses, one for top switch and the other for bottom switch. Next two inputs are plus or minus 15 volt DC supply, and one input is the common point of the plus or minus 15 volt DC supply. This holds good for the other two phases as well. Now, we will see what kind of control loops are programmed in the Opal RT to control the inverter. We all know that solar inverter works with two configurations commonly. One is single stage conversion, while the other is dual stage conversion. In single stage conversion, PV panels are directly connected to the inverter DC bus, as there is only one conversion stage. The device switching and conduction losses are quite less. This results in improved efficiency and reduced cost. In case of a dual stage conversion, first there will be a DC-DC stage to extract maximum power, followed by DC-AC stage. For single stage conversion, the control system is shown here in the given slide, which consists of an MPPT stage followed by DC link voltage control and current or power control loops. Apart from these loops, grid synchronization loop using phase locked looped so called PLL helps in synchronizing inverter with the grid voltage before feeding power to the grid. This MPPT block gives the DC link voltage reference so called VDC link star. The DC link voltage control tracks the voltage reference by providing the current reference ID star. The innermost current loop tracks the reference current to deliver the maximum power. Note that the control system is implemented in DQ frame with synchronous reference frame of the PLL. Here ID star represents the D axis reference current, which will control the active power. Similarly, we can control the reactive power injected to the grid so as to provide voltage support by tracking the reactive power reference QAC star. In the dual stage conversion, DC-DC stage has MPPT block, PV voltage control and current control loops, while the DC-AC stage resembles the one in single stage conversion, but here in this demonstration our focus will be on single stage conversion only. Now, moving to the hardware demonstration. Now, before going into the demonstration, let us have a look at the hardware connections. The PV emulator is connected to the DC input terminals of the IGBT stack. The AC output terminals, that is RYB phases, are connected to the L filter. For each phase, we have connected two such inductor boxes in series to form total inductance per phase 6 millihenry. The other ends of the inductors is connected to the point of common coupling PCC formed by this MCB. At this MCB connection, bulb loads are connected in parallel path and they act as a load. The other side of the MCB is connected to the output side of the grid emulator, while the input side of the emulator is connected to the distribution system of the campus. Also, notice that after inductors, the wires are passed through the LEM current sensors. For voltage measurements, sensing is done near MCB input and the sensed signals are connected to the LEM voltage sensor board. The setup is ready for demonstration. The control loop is enabled, the synchronization to the grid voltage is ensured by the PLL. The MPPT and DC link loop will track the maximum power giving the reference current, and the current control loop will further track the reference current. So, in this way maximum power point is getting tracked. We can see the 3-phase inverter output current waveforms are captured in the DSO. The current that we are seeing is fed to the distribution grid via grid emulator. Now, the irradiance is varied in steps and the corresponding inverter output currents are captured in the DSO. Thank you very much.